Hi everyone, welcome to part 2 on our video of integration techniques. Now let's go ahead and begin this video by taking a look at the integral of x squared divided by x plus 4. Now I mentioned here that u substitution should always be our go-to, but I'm hoping that you can easily see that a u substitution where we pick u as the denominator wouldn't quite work. Now I'll let you guys see why, but okay, so u substitution doesn't quite work. It's not like we can go ahead and split up the numerator. So what can we do? Well, I want you guys to notice here that the degree of x in the numerator is 2, while the degree of the denominator is 1. Okay, so recall here that if you happen to notice that the degree of the numerator is greater than the degree of the denominator, then this is a perfect example of an integral where we can use polynomial long division. So put here as a strategy, long division. Okay, so let's see, how did long division work? Well, in this case, we are dividing an x squared by an x plus 4. And we want to figure out, okay, well, what would we need to multiply an x in order to get an x squared? Well, we can go ahead and multiply an x by an x to get an x squared. So x times x squared, that's going to be an x squared, but we're subtracting. Then an x times a 4, that's a positive 4x, but we're taking away a 4x. Now once we subtract, this gives us here a negative 4x, and now we repeat the process. What would we need to multiply an x to get a negative 4x? Well, we need to multiply the x by a negative 4. So negative 4 times x, that's a negative, but since we're subtracting, then this one here is going to become a positive 4x. Then a negative 4x times a 4, that's a negative 16. But because we're subtracting a negative, well then that just pretty much turns into addition here. So we're left with a 16 here as our remainder. So the resulting quotient is x minus 4. So we can go ahead and rewrite this integral as the integral of x minus 4 dx plus the integral of the remainder here. Now something very important here, once we rewrite the remainder, don't forget, we are dividing the remainder by the original divisor, which in this case was x plus 4. And there we go. Now with the use of polynomial long division, we turn this problem into two separate integrals, but these two separate integrals themselves are not too bad to solve. So let's go ahead and solve them here. Just moving things around here a little bit. Alright, so if I want to focus on the first integral, what is the integral of x minus 4? With respect to x, that's going to give us an x squared over 2 minus a 4x. And I'll have to see later once we're done with the other integral. So what about the integral of 16 over x plus 4? Well, for this one here, we can go ahead and take out the 16, and we're left with 1 over x plus 4. Now at this point, we can go ahead and use a u substitution here. So if we let u equals to x plus 4, then the du is simply 1 dx. Oh, well, look at that. It seems like we're going to be getting a nice integral of 16 times the integral of 1 over u du, which very similar to the ones that we've encountered. We encountered it quite a bit in this section. That's going to be 16 times the ln of the absolute value of u. But in this problem though, once we substitute in the u, since the inside, the u could be negative, I'm going to rewrite it here as 16 times the ln of the absolute value of x plus 4. Alright, so now that we've done both integrals, we can go ahead and put everything together here. I'm just going to give myself a little bit more room. So our final answer is going to be equals to x squared over 2 minus 4x plus 16 times the ln of the absolute value of x plus 4 plus c. And there we go. We've done with the integral. So as you can see here, guys, polynomial long division, if you didn't remember it, it's not too bad. Pretty straightforward almost. Alrighty, so now let's take a look at our next integral, where we have the integral of 1 plus e to the t squared divided by e to the 4t. Now, if we take a look at this integral here, it doesn't seem like a u substitution would be, all that helpful. So what else can we do? Well, for this one here, I want you guys to take a look at the techniques that we went over in the previous video and see which one do you think it would apply. Now, I'll pause the video here, take a look at those strategies, and see which one do you think will work. Alright, so hopefully you recognize that the strategy was to expand the numerator. Now if we expand the numerator, what will we get? Well, this problem here wants us to square the 1 plus e to the t squared, which means that we're multiplying it by itself. Now I'll let you guys verify that once we square, we should be left with a 1 plus 2 e to the t plus e to the 2t. Okay, so rewriting our integral, we're going to have the integral of 1 plus 2 times e to the t plus e to the 2t divided by e to the 4t. So what can we do now? Can we go ahead and maybe use a u substitution? Could we integrate it right now as it is? Well, maybe you realize that, hey, well, it looks like we can actually use another strategy. Now that other strategy here is to separate the numerator. So this is going to give us then a new integral. It's going to be the integral of 1 over e to the 4t plus 2 e to the t divided by e to the 4t plus e to the 2t divided by e to the 4t. Now before integrating though, I think we can simplify it a little bit more, and this is going to give us the integral of e to the negative 4t, I'm just rewriting it here, plus 2 e to the negative 3t plus e to the negative 2t. Alright, now performing these integrals with ease, not too bad. It's going to be a negative 1/4 e to the negative 4t minus 2/3 e to the negative minus 1/2 e to the negative 2t plus c. And there we go. We got our final answer here. So as you can see for this one here, it was a combination of strategies, but lucky for us, we were dealing with integrals of exponentials, so these ones here are not too bad. Alrighty, so now let's take a look at one more problem here, where we have the integral of 1 over the square root of y minus 4x minus x squared. So how can we handle this problem? What would be the strategy? Well, one thing I noticed for this one here is that I have a square root in the denominator. Now whenever we have a square root in the denominator, I always associate them with the integrals of either the hyperbolic functions or the inverse trig functions. Now, the thing about those ones here is that they had very specific formulas which sometimes required us to have either a difference of squares or a sum of squares in those radicals. But as it stands right now, well, I don't have a sum of difference of squares. Instead, I have here a trinomial. Well, as you may have expected or you might have guessed, what we can do here is complete the square. Okay, so I'm going to go ahead and complete the square on the expression 1 minus 4x minus x squared. Now first I'm going to go ahead and rewrite it here as negative x squared minus 4x plus 1. Okay, now remember when we're completing the square, we typically want to have a coefficient of 1. Now this one here is not a coefficient of 1, it's a negative 1. So what I'm going to be doing here is I'm going to go ahead and factor out the negative, but only on the terms with the x's, both the x squared and the x. So I'm going to have here a negative parentheses x squared plus 4x, and then this plus 1, I'm going to leave it here, minding its own business for a while. Alright, now we're going to be focusing on completing the square inside this parentheses. So complete the square here. Alright, so if we're completing the square, then we're going to have a negative, I'll use a bracket here, x squared plus 4x. Now the term that we need to add to complete the square should be a b over 2 squared, so it should be a 4. But what I'm going to be doing here is a trick of essentially adding a 0. If I add a 4, then I also need to subtract the 4 in order to keep the equation or the expression the same. Alright, so I'm going to close this parenthesis here, and we're still adding a 1. Now at this point, I'm going to recognize the fact that, hey, well, since we added a 4 here, this is a perfect square now. So we completed the square. So now I'm going to go ahead and rewrite this one here as a negative that's multiplying my perfect square here. So negative, I'll open up here the parentheses x plus 2 squared. That's our perfect square here. Then I'm also going to distribute this negative to the negative 4. It was still inside that bracket, so it actually becomes a plus 4 plus 1. Now, rewriting everything here, we have a negative parentheses x plus 2 squared plus 5. Now, with this new form, I'm going to go ahead and rewrite the integral as the integral of 1 over Now we're going to have the square root of. Now for this one here, I'm going to switch the order a little bit. I'm going to rewrite it here as 5 minus x plus 2 squared dx. Alright, so now that we're left with this new form of the integral, what can we do? Well, I want you guys to remember that we actually have encountered integrals of this form. And in fact, I'll write the formula here. The formula that we will be using for this problem is the integral of 1 du all over the square root of a squared minus u squared is equals to the arcsine of u over a plus c. Okay, so in this problem, we get to see here that it seems like our a squared is the 5, and our u is simply the x plus 2. Put it here. So let's see what we would get then. Well, we're going to get, I'll put here the a being 5, our u being an x plus 2. Then for our final answer then, we're going to have the arcsine of our u, which was the x plus 2, divided by our a, which was, whoops, not my bad here. The a was not 5, a squared was 5. However, our a is the square root of 5. And there we go. Now we add the plus c, and our final answer here is this one. And for now, we are done here, guys. Now in the next set of videos, we will be discussing new integration techniques, but this one here was just a review of techniques that can help us rewrite an integral in a different form than we're actually able to solve. Alrighty guys, well, I'll see you in the next video. Have a good one.